time. And from there, we take it from there. So last time we spent more proving that a closed interval of R is compact. Arbitrary closed interval AB, but we fix A equal to 0 and B equal to 1. And from there, we constructed a set, and we proved that that set was exactly the interval, the closed interval 0, 1. And that set was what? This was the idea. We took the set of points anyway. We took a subset. We denoted that by, was it K or M? Okay, we constructed a set and we took it as a subset of the closed interval 0, 1, right? So we took it to be the set no. We took it as this the point X in S. We call it S if I'm not mistaken. We took it M. Let's say that the name was M equal to the set of S in the interval A 0, 1, such that the closed interval 0S has a finite number of covering by open intervals. So we first took a covering of the interval 0, 1 by open sets, right? And we want to prove that that interval 0, 1 has a subcovering. Of course, from this covering, we can extract the subcovering that will still cover the closed interval 0, 1. So now what we did, we constructed a set M, which is the set of S, such that the closed interval from 0 to S is contained in a finite number of open set from that initial covering. So if we succeed to prove that this M is the entire interval 0, 1, we are done, because it will mean that 0, 1 is covered by a finite covering. So that's what we did. And we saw that it was not empty, because if we take S equal to 0, the closed interval 0, 0, which is reduced to 0, is in, we can find a single open set that contains 0, and that is finite, so it's non-empty. So that's how we proceeded, and we succeeded to prove that it is reduced to the, we even showed that it was an interval, right? And if it's an interval, it means that it can be written in the form 0, a certain number, 0 what? 0, maybe K, where K is the max, right? It's the max of the subinterval, right? Of that subinterval M itself, right? If you take the max there, it will be that interval. And then we show that that upper limit is 1. And we succeeded to prove it. Okay, so that's what we did last time. But before last time was only for the tutorial. But before that, the last notion that we covered was the notion of the metric space, right? Metric space. And we say, what is a metric space? It is a pair of a set and a distance defined over the Cartesian product of that set with itself, right? That satisfies the property that the function, which we denote by the distance, is a function of two variables, x and y. It's first of all positive, because if you have to measure the distance between 2 points, it has to be positive. So it has to be positive, it has to be symmetric, and the distance from x to y is the same as the distance from y to x, right? You have, that's the second, positive, symmetric, right? Triangle inequality, that is, to move from A to B, if I pass to C, the distance from A to B will be less than or equal to the distance from A to C and then from C to B. That's what we call the triangle inequality. So, or which other, yeah, I think these are the main properties of the distance. I hope I have not forgotten any. Yeah, and we'll look at a few examples which are on the note, and I ask you to read and try to do the proof. All right, so what we are going to do today, we are going to see how a distance can define a topology. How do we define a topology from a distance or a metric, right? Because a distance is a metric. So if I have a set to which I endow a distance, it becomes a metric space. Now, from that metric space, can I generate a topology? Is there any underlying topology? Because that's the right word, underlying topology. Is there any underlying topology defined by a metric space? Yes, there is. And the easiest way to do that is, first of all, to define what is an open set or an open ball. All right, we can define the ball, right? Because we have already a metric, right? We can define a ball center at this particular point as the set of all the points that are less than or equal to the radius, right? Then we have a closed or open ball depending on whether the radius, the point at the radius at the boundary are included or they are excluded. We have open or closed ball. So when we define the balls, finish from those balls, now we can generate an underlying topology. That's what we are going to look at today. Really interesting. Okay, from the property of the distance, when I recall the various property, I forgot to mention this one, that the distance between 2 points is 0 if and only if the 2 points coincide. Yeah. Good. So underlying topology to a metric space, incompleteness. Topology in a metric space. So we have a metric space, we define a ball. This is what I was talking about, right? A ball center at X or and of radius R. So you have an open ball, you have a closed ball, right? Open is when you have a strict inequality, so that, okay, so a ball center at X and of radius R is the set of Y in E, right? The set in E such that the distance from X to Y is less than R. So this is an open ball around X or center at X with radius R. So this is open ball. So we already have the definition of an open set. Of course, it's not a general open set, but we call it open ball, right? Of course, which is a particular form of an open set. Because once we have a topology, we know that a countable union, right, is still there, something like that. The countable union of open is open. So that's part of topology. Okay, so this is a particular form. And this is in fact the basis, the basis for open sets. Okay, now this is how we define the topology on E. So T, the topology on E, is defined as all the subset of E that are neighborhood of each of their points. You remember how we even characterize the topology of R. We say that we know that a set is open if it is the neighborhood of any of its points, or neighborhood of all its points. That's exactly what we are doing here. So we take the open set of our topology to be subset of E. That you can see O. You see for each X in O contains its neighborhood, one of its neighborhood, right? You can see here. When we take for each point, we say we can find a radius such that O contains an open ball and an open ball centered at X. So you mean that O, this open set, is a neighborhood of each of its points. So that's how we define an open set, right? Or the open sets of the topology. All right. So once you have the topology, everything that we cover concerning topology will also apply to this, meaning that you can define a neighborhood, you can define convergence sequence for this topology, you can define compact set, you can, anything you can imagine about topology, we have an underlying topology now here from the metric space, so you can do that. So every metric space is a Hausdorff. We did that for R. You can repeat exactly, you can follow the same procedure, but instead of taking our opens as we define, we define opens using using open interval. Then you just replace those open interval with open balls. That's all. The proof will be exactly the same. You take 2 points, x1, x2. X1 is different from x2, meaning that the distance from x1 to x2 is different from 0. So that distance, you call it d. D is the distance from x1 to x2, right? Because now here we have the notion of the distance. And the distance is in R was just the absolute value between the two. Now you can say distance d, x1, x2 different from 0. Then you take your epsilon to be less than that distance by 2. Right? And then you can construct the ball, right? For each of the points, you can take the ball center at x1 and of radius, you take a radius that is less than the distance by 2. For each one of them. Finish with that, you follow exactly the same proof, and you'll be able to show that every metric space is Hausdorff. Okay, now here we have an arbitrary topological space, right? Which is not an underlying topology from a metric space. You just have an arbitrary, let's say you are given an arbitrary topological space, and you want to find out if it is metrizable. What does that mean? Metrizable means that it comes from a metric. It means that it can be considered as an underlying topology of a metric space. That's what it means to be metrizable. Right. Okay. Now, this is the definition. A topological space, Xt, is said to be metrizable if the topology T can be specified by means of some metric, exactly what I said, can be specified by means of the metric. That is, if the topological space is homeomorphic to some metric space. Homeomorphic to some metric space. Meaning that we can find an homeomorphism between Xt and a certain metric space E, D. Right? That is the pair E, the set, D, the distance. So we can find an homeomorphism between these two spaces, then we will say that our topological space is metrizable. Right. Now we have an example here. Example, the topological space X T sub T is not metrizable. Where T sub T here is what? Sub T here stands for the trivial. If you remember, we saw that we have the discrete topology, the discrete topology and the trivial topology. And what was the discrete topology? The discrete topology was the topology Px. And the trivial topology was what? Was the topology that consists of the empty set and the set capital X itself. That's what we call the trivial. So here we are told that the trivial topology is not metrizable, right? Why? Because it's not Hausdorff, right? Because remember that in the definition of metrizable, we say that it can be homeomorphic to, it is homomorphic to a metric space. But we know that every metric space is Hausdorff. If it's Hausdorff, by the homeomorphism, the structure of the metric space will be carried out into that particular topological space, right? So meaning that if I have a topological space that is not Hausdorff, consequently it cannot even be metrizable. So that's a simple thing. Okay. Now, there are properties that are only specific to metric spaces. We can have a topological space that is metrizable, right? As we mentioned here, that the converse is not always true. That is, an arbitrary topological space is not metrizable or does not it's not metrizable. I think that's the simplest way to put it. Okay. Because we saw that a metric space can define a topological space, right? I mean, has an underlying topology. So once you have a metric space, all the properties of a topological space will apply to it because it has an underlying topology. As a topology, the underlying topology as a topology has all the properties of a topology. But there are properties that are only specific to metric spaces that you cannot transfer to an arbitrary topological space. And that's what this means, that the converse is not always true. So meaning that there are properties that are only specific to a metric space because you have a metric, but in a topological space that is not metrizable, there are properties that will never apply in that topological space, right? For instance, this case of Hausdorff, you see, that's specific to a metric space, right? We saw that the trivial topology, for instance, since it's not metrizable, it cannot be Hausdorff, but Hausdorff is a property that is intrinsic to a metric space, right? But that's just an example that I took, but there are many other properties that we'll see only apply to matrix spaces, and we are going to look at some of them. Okay, so the following definition is about equivalent distances. So two distances are equivalent if they define the same topology. So let's say I have D1, which is a distance. I have another distance D2, right? We know that if you take the metric space E with D1, that is endowed with the D1 distance, and the same metric space E, but this time with D2. You see that if you take the underlying topology endowed by D1 and the one endowed by D2, these are two different topological spaces, right? They're different because D1 and D2 are two different distances. Now, those two distances D1 and D2 will be said to be equivalent if the two underlying topologies are the same. What does that mean that they are the same? If they have the same open sets. Because if you have the same open set, you have the same topology. Because remember that a topology is defined by what? By open set. So if you have the same open set, you have the same topology. Right. So that is the definition of equivalent distances. And the next definition is distance preserving or isometry, right? So we have two metric spaces, X with D sub X, Y with D sub Y. So those are two metric spaces. Now we have a mapping F from X to Y. That is, we can say from the first metric space, X dx to Y dy. Those are two metric spaces, and then we have a mapping between the two. Now, that mapping will be called an isometry. Isometry means that same metric, same metric, in fact, iso, same metric. It doesn't mean that D1 and D2 are the same, no. It just means that if I take 2 points, the distance between 2 points in the first space X, I take the images. Let's say I have X1 and X2 in X, the first space, right? Of course, the distance there will be dx. Now, if I measure dx, X1 to X2, so that distance, the distance from X1 to X2 in the first space, that is dx, X1, X2. Now, if I take the images, the two images of X1 and X2 by F, I will call the images Y1 and Y2. Those are the images in Y. Now if the distance between Y1 and Y2 in the second space is the same, you have the same distance, meaning that the distance that they had in the first space is exactly the same when I transform them. The distance is preserved. So if this is true for any two arbitrary point in X, then we say that that F is an isometry because it will not deform, or it will not modify the distance that these 2 points had in the source space, right? Because I can call the first the source space and the other one the transform or the destination space. I will take a simple example to show you. I will give you an example of an isometric. For instance, let's say a rotation. You see, this is my phone. If I take any point here, two arbitrary points on this tablet, two arbitrary points, I measure their distance from, let's say, X1 to X2. I measure the distance. Now, if I take this, I translate, or I rotate, you see that the point will not change, because if I translate, the 2 points are still there at its exact position. Now, if I translate, you see that the translation is a function. I move from here to the next position, I measure again, it will be the same. Now, if I even keep it, the 2 points there, and then I rotate, the distance will still be the same. So translation and rotations are isometric. These are just a few examples that I took. So that is the idea. So here I have x1, x2, I measure the distance between the two. And then I take the image, f of x1, f of x2, and measure the distance. If this distance is still the same, then we say that f is an isometric. Okay. And isometry is necessarily injective. That is a one-to-one. And this is the proof. Easy, right? If it is an isometry, to show that something is injective, I take x1, x2, I assume that f of x1 is equal to f of x2, and I have to show that x1 is x2. If that is true for two arbitrary elements x1 and x2, then f will be called injective. Okay, now we assume that f of x1 is equal to f of x2 and that f is an isometry. Now, we compute the distance from f of x1 to f of x2. Because it's an isometry, it will be the same as the distance in x between x1 and x2, right? And this distance is 0. Why is it 0? Because f1 is equal to f2. So we know that the one property of the distance is that if 2 points coincide, the distance between the two is 0, because it's the same. Distance from x to y is 0 if and only if x is equal to y. But because f of x1 is equal to f of x2, the distance from f of x1 to f of x2 will be 0. So that's what we have here, right? This distance, which is equal to this, is 0, right? And we know that because the distance from x1 to x2 is 0, x1 is equal to x2. So that's why we say an isometry is injective, or a one-to-one function. So that is a simple proof, right? Just to rewrite things properly. Okay, now the next thing. So we mentioned isometric function here. Right? A map is called an isometry or isometric function, or distance preserving, if this is true. Now we are going to define something else here, right? Two metric spaces x dx and y dy are said to be isometric. Now we are talking about two metric spaces that are isometric. It's not about a function that is isometric or distance preserving, but now we are talking about two different metric spaces that are isometric. So now we will say that they are isometric if there is a bijective isometry from x to y. In other words, if we can find a mapping f from x to y that is isometric, not only isometric but also bijective. We know already that an isometric is injective, so it just needs to be an onto, that is a surjection, right? That function, that isometric function, has to be surjective because we know already that it is injective. So if it's surjective, it will be a bijective isometry. Okay, another definition is the concept of Lipschitz continuous function. So similarly, if we are given two metric spaces and we have a function f from the first metric space to the second one, that is from x to y, the function will be said to be Lipschitz continuous if there exists a constant k positive, which is called the Lipschitz constant, such that for any two arbitrary points, x1 and x2 in X, we have this inequality. That is, the distance in Y, that is the target space, between f of x1 and f of x2 is less than or equal to k, that is a factor of the distance in X between x1 and x2. So if this is true, we say that f is a Lipschitz function. Obviously, in numerical method 1. Numerical method 1? Yes, I think it was numerical method 1, yes. In the tutorial, we defined this Lipschitz function. Yeah, in one of the tutorial, numerical method 1, we defined that. Okay, now if this k is in between 0 and 1, of course, it has to be positive, right? Because it cannot be less if this is negative, right? It has to be positive, right? Okay, so that if this k is less than 1, we say that the function f is a contraction. Contraction. How do we see the contraction? The contraction, it means that, let me take the case of my tablet again. See, if I have 2 points here, and then I perform a transformation to this. And now, it turns out that when I transform it, in the range there, when I measure the distance, it turns out to be lesser than the original distance. We say that it has been contracted. So the function that will perform this transformation will be called a contraction. Right, a contraction. Let me take another example. Okay, squeezing. Let's say, for instance, I have maybe not this, right? Because it is really rigid. This is rigid. I assume that I have something that I can easily compress, right? If I take something that I can easily compress, let's say that I have this. Then I take the distance between 2 points there, and then I perform a transformation to this by squeezing it, right? Or by squashing. If I squash this, and you look back there, you will see that the distance will be, right? Of course, it will be deformed. But let's say we have something that we can easily squash, right? Then it compresses the distance, and the distance becomes smaller. We say that it's a contraction. Now, what if it's like an elastic that I can stretch, right? It will be magnified, right? We say that instead of compression, it will be an extension, you see. So those are the type of situation that we can have. So if that case greater than 1 is no longer a contraction, right? Instead of being a contraction, you can say that it becomes an extension. Contract, extend, extension. Okay, so I will skip this example. I will go to something else. I'll go to another definition. Okay, convergence. Now that we are dealing with metric spaces, you can see how we define the convergence sequence in terms of the distance, right? Because here we're in, okay, so using the underlying topology of a metric space, we can reformulate the definition of a converging sequence, right? Okay, so a sequence Xn in a metric space ED is said to converge to a point X in E if every open neighborhood of X0, that is B sub epsilon of X0, contains all point Xn starting from a certain index. That's exactly what you usually write, what you wrote in R. Now for any epsilon positive, there exists a rank from which all the terms of the sequence will be. Okay, let me write it for R. In R, this is what you will say. So here you will just say, this will imply okay. So in R, this you say implies that the distance for that absolute value, X minus X0 less than epsilon. This is exactly what you wrote when you, in fact, a converging sequence in R, in real analysis, this is how you write it, less than epsilon. And we also saw that this also means that Xn will be in the open interval X0 minus epsilon, X0 plus epsilon. So this is an open interval. But now, in our case, in the case of our metric space, what does this mean? From this one, this means by definition of ball, this one. It just means that Xn belongs to what? To this ball, this the B epsilon X0. Exactly like here, this is what? This is interval. I can write this as interval center at X0 and of length of radius, if you want. That is that's not the total length, because the total length will be 2 epsilon. No, not 2 epsilon. What am I saying? It's epsilon. Yeah. It is center, interval center, and of length epsilon, but the total length, because this is what we have here. We have this open interval. This is X0, the center of the interval. Now this point is X0 minus epsilon. So the length from here to there is epsilon, and then from here to there is another epsilon. So if you add epsilon to the center X0, you are at this point. X0 plus epsilon. If you subtract epsilon, so this total length, like this, is 2 epsilon. So the total length of the interval is 2 epsilon. But now if you consider as radius, that is the distance from the center to one extreme position, or from the center to one endpoint, is epsilon. That's why we call it radius. But the total length is like the diameter of the interval is 2 epsilon. But the radius of the interval is epsilon. So I'm using this analogy for you to understand when we talk about ball. And for the ball, instead of interval, now we are in a space. We are no longer on a, of course, this ball, if we are in a one-dimensional space, like in R, this open interval will coincide exactly with this open, this open ball will coincide with the open interval. Now, if we are in R2, it will coincide with what? A circle, center at X0 of radius epsilon. So the radius being epsilon, the diameter will be 2 epsilon. So that's the connection I want to show you. Now, in R3, we will have exactly what we call the ball, right? It will not be like a disc or a circle. When I say circle, it means that's just a boundary, but I wanted to say a disc, right? In R2, it will be a disc. In R3, it will be a ball, like the ball, right? I don't have a ball here, unfortunately. A ball like this, a white ball like this, a ball. That will be in 3 dimensions. Okay, I hope with this explanation you have a better understanding of the metric space. We are dealing with balls now. So that's how you write the converging sequence. You can see that this reduces to what you know in R if this is a distance in R, that the absolute value. So we are moving from R and we try to generalize the concept of converging sequence to a more abstract space. That is exactly the procedure. We are moving one step further to make the concept that you know in R more abstract, R, Rn, all the knowledge that you know in R or Rn, we want to carry those structure or those concepts in a more abstract space. Okay, now this is what we call sequential convergence, right? It looks like, anyway. Okay, so proposition, a sequence xn converges to x0 in the metric space ED if and only if the limit of the distance from xn to x0 when n goes to infinity is 0. And this is very important. This is a very important statement or result. If you want to show that a sequence converges, let's say sequence xn converges to x0, if you can just show that this is true, this limit, right? Just prove that the limit of the distance between xn and x0 is 0. Then you're done. You don't need to do all these things that for any epsilon there exists, blah, blah, whatsoever. You can prove this straight. Maybe still be using the epsilon whatsoever, because this limit is exactly what is written here in the definition of converging sequence. It's exactly the same. But if you have the definition of the distance, for instance, and you can just take the limit straight forward and show that it's 0 without having to take epsilon positive and show that you can find n such that this will be straightforward, right? So that's why I say it's a very important result. Right? It's an important result. Let's, for instance, look at, I remember that the way. Okay, look, for instance, here. Let's say that you are given a distance like this, right? You see that you have the expression of the distance. If from this you can show directly that is the sequence x will convert towards something, you take the limit of this because you know the distance is given. If you can take the limit here directly and show that it gives 0, it will be straightforward. So similarly with this one or that one, you can take the definition of a sequence, substitute there, take the limit here directly and show that it's 0. You don't need to go through all this hassle of taking epsilon and all that. If you can do that straight away, it's fine. So it can be useful directly. This one can be useful in many situations. Okay, now the second result is about continuity. If I have two metric spaces, x, y, and I have a function defined from x to y, I want to show that it's continuous. Right? I just show sequential continuity. If I want to show that it's continuous at an arbitrary point, let's say x, if I can show that for any sequence xn converging to x in x, f of xn will convert to f of x in y, then I will conclude that my function f is continuous. Right? So this is a good result. This is what we call sequential continuity. Okay, another theorem. We are given a metric space ED, and A is a subset of E. Lowercase a is a point of E, right? So, and we assume that it is a limit point, that A is a limit point of capital A. And the set of limit points are denoted by A prime. Okay, so this theorem tells us that a point is a limit point, that if A is a limit point of capital A, if and only if you can find a sequence Xn of distinct points that converges to A. Okay, so you have accumulation point and you have limit point. For accumulation point, you can find a sequence like this that will converge, and you don't need the point to be distinct. But now, an accumulation point will become a limit point if all the points of the sequence are distinct. You can go to the definition of limit point or accumulation point. You'll be able to see that in the case of limit point, all the points of the sequence have to be distinct. Whereas for accumulation point, you don't require the point to be distinct. Right? Okay, so that's for this theorem. And there's a problem here. I encourage you to try to do this problem. Okay, now we are going to define what is a Cauchy sequence, which you know already from real analysis. Real analysis. This is the definition of Cauchy sequence in R, you know. But now you can see that we will replace this by the distance between xn and xn, less than epsilon. So let us go to the definition. A sequence xn is called Cauchy sequence. If for any epsilon positive, you can find a rank such that for any mn greater than n, the distance from xn to xn is less than epsilon. So that's exactly similar to what you wrote in R, right? In real analysis, you just convert or transform this distance to this, because this is a distance in R. In R, it's already written here. That's exactly what I wanted to write. So in R, the distance from X to Y is absolute value of the difference. That's exactly what I know. You just change that into the distance notation. Okay? But because we are not in R, but this distance will be in an abstract space, which we call a metric space. So we replace this with that. Yeah. So as we will see later on, okay, we'll come back to this later on. Okay, if you are not in R, this distance will be replaced by the norm, right? The norm of the difference between X and Y, right? If you are in a norm space, the distance can be represented by this. Okay, now a metric space is called complete if all Cauchy sequences of element of E converges in E. That is, the limit point is still in the space, is still in E. Because the limit point might be out of the space, right? It might be out of the space. So if the limit point is still in E, right? Then you will say that the matrix space is complete. So we know already that R is complete. I don't know if that's how you call it in real analysis. Maybe, yeah, I assume. Because in R, remember that in R, every converging sequence has a limit in R. If you take a sequence in R that converges, necessarily you say that it converges because the limit is less than infinity. Something that is less than infinity, a value that is less than infinity is in R, because R, the limit of R is infinity. You just exclude infinity from R, right? So if something, you say that something diverges because the limit is infinity, but infinity is not an element of R, then you say it diverges, right? So R is complete because every Cauchy sequence of element of R converges. And you prove it in real analysis. Okay, so that notion of R, we bring it also in a metric space. And if every Cauchy sequence of element of a metric space converges and the limit is still in the metric space, we say that that metric space is complete. And I take the opportunity to already introduce what is a Banach space, because Banach space is the one core concept that we encounter in functional analysis. Now, Banach space now is simply it's a complete metric space. But now the metric space here is defined by a norm. That's all. A Banach space is a norm space, whereas a metric space is not necessarily a norm space, because a distance is not necessarily a norm. Now, if you have a norm, from the norm you can construct a distance using exactly what I wrote here, right? The absolute value x minus y is the distance from x to y. But now if I'm in a norm space, I replace absolute value by the norm. I can define a metric from a norm, right? So if I'm in a norm space, let's say we have E and we have a norm. We define what is a norm. So if this is a norm space, from this norm, I can define the distance. We just define the distance from x to y to be the norm of the difference x minus y. Exactly what we did here with R. So that's how you obtain a distance from the norm space. So once you have a norm space, you have a metric space. You just define the distance from the norm this way. And now, if this metric space is complete, you call it Banach space, right? So Banach space is a complete metric space, but where the norm is defined, where the distance is defined from a norm. So that is it. So you already know what's a Banach space. The only thing we need to know now is the definition of the norm. Once we know this, we will know what is a Banach space. The other thing we need to do stage. What do we need here? Compact matrix space. We know already what is a compact set. We did that. Yeah. So I think the rest you can just read. You can read the rest. And I would assume that you read and that this has been covered. The next thing we would do, right, next time, we are going to go through examples. I think what I will do next time, when I say examples, I want to go straight into Banach space and use concrete example to show you how to proceed if you want to show that something is a Banach space. That is, you take a Cauchy sequence, you show that it converges and that the limit is still in the space. So as an application to this, I think it will be better to dive straight into Banach space and tackle some of the examples. Okay, so for the application of this concept of a complete matrix space, we have the example of R. Also, C with D infinity. Among the example, when we define distance, we have D infinity somewhere here. I think it was defined, D infinity. D infinity is this one. The max, the max. That's what we call D infinity, this definition, max. See, this is C, continuous function on the interval AB. We have the max. This is what we call D infinity, max. So this, if you take this space E with this distance, D infinity, is complete. It's a complete matrix space. Yeah. So it is complete. But if you take D2, that is D2, exactly what we did in numerical method. D2 is the 2 norm. I mean, when I say 2 norm, I'm already talking about norm. Even norm, we did that in numerical method. What was I even saying that I would define what is a norm? From numerical method, we define what is a norm, right? So you know what is a norm. I don't really need to do that again because in numerical method 1, it was even 1. Numerical method 1, we saw what was norm. Norm of vectors, we defined that norm of vectors. And after that, we define norm of matrices. So you know what it is. So when I say D2, this is D2. D2, so if I'm here for 2 functions, D2 F1 like this. What is it? It is, we can take the integral. D2, okay, we can take this. From A to B, okay, we are in the interval AB. The integral from A to B, absolute value f of x dx minus gx like this, square dx like this, and then we take the square root. So this is what, okay, it's similar to what we know from vectors. You see that the summation here, if you recall the two norm, if you recall the 2 norm of the vector, let's say this vector is in Rn, right? The 2 norm, if you recall, we said that it was the sum like this, absolute value xn square, and then we took the square root. And remember, I said that if you want to define the distance from between 2 points, you can take it to be the norm like this. That is it. So this is, if this is D2, we put norm 2 there, right? So, but because these are not vector, but these are continuous function, and continuous function are integrable, so you transform the sum into an integral. So that's how you define the 2 norm, or D2. D2, this is how you define it. Take the square root. Okay, let's move, let's scroll up and check if that was defined above. It was given among the, yeah, it's here. We even call that D sub P, where P can take the value 1, 2, 3, or so. This is D infinity. It's even there, it's defined, yeah. It's the max, and GP is exactly this. So if you take f, x equal to f, y equal to f, transform that into function, then you convert this summation into integral, and then that is it, you have it. Good. So you know many things anyway. You know many things. You just need to put things Okay, so I think that one thing that we will do next time will be to do this example. All right, to show that this is complete and this one is not. Okay, so I promise we will cover that. But read the rest of the slides, right? Read this. I assume that it is covered. We will be using those results later on, but read and go through. So what I promise for next time will be to show this result. We are going to do this together. Okay, so we'll stop here for today. Thank you so much for your kind attention. God bless you. See you next time. Maybe I will record another video by Friday. And don't forget your test, because you really need to write already test 1. So let me know if you can write it. It will be online anyway. If you want to write it on Saturday or Sunday, just let me know. Right? Send me an email to confirm at what time on Saturday or on Sunday you want to write a test. It will be an online test, test 1. So it will cover everything from the beginning up to metric spaces, but we will not do what we covered today. That is Banach spaces or complete metric spaces. No, we will not cover that. But the rest, everything that we covered, except what we covered today, everything else is expected. And some result of also of real analysis, right? You need to know your result of real analysis because it's a prerequisite. So all those results from real analysis, prerequisite, you're supposed to know that. If you need a catch-up session, maybe a tutorial session for us to have this tutorial session together where you can ask your questions, or we can cover some, you want to ask questions about some difficulty you had when you were going through the tutorial, please let me know so that we organize a session maybe Friday evening before the test or something like that. Please let me know. Send me an email to let me know. Okay, thank you. Bye.